and welcome to the final presentation of this year's student conference, Technology and Challenging Environments. Today, we'll explore the application of various technologies, a range of different scales, for environments that push the limits of innovation and resilience. The 7 speakers will take us from the immense scale of wind turbines and their battles with the forces of nature, photovoltaic water pumping systems and their applications in rural and desertic areas of sub-Saharan Africa, all the way to minute energy storage devices implantable inside the human body. So, I know you're eager to hear about all these topics, so without further delay, I'll pass you on to our first speaker, Declan, who will kick us off by talking about the impacts of wave-breaking loads on offshore wind turbines. Over to you, Declan.
Thank you, Dupont, for that introduction, and thank you to you all for still being here with us. As he mentioned, my research is on simulating wave-breaking loads on offshore wind turbines and comparing against design solutions. So I can already hear you asking, why do we need to think about this? I can go to the beach and relax let the waves wash over me for hours without getting destroyed. Surely these massive steel structures can withstand the wave loads. But the difference between you having a nice day at the beach and these wind turbines is that the waves they face can have the same impact force as a pickup truck hitting them at 60 kilometers an hour. Now, fortunately, there are existing design standards that take this into account, but those design standards are based on regular waves, which they may be easy to simulate, but mathematically, but unfortunately, they don't exist in the real world. So my aim with this project was to improve the existing design standards for these slamming loads by taking a look at and simulating irregular waves and then comparing the results from that to the regular wave design standards, and specifically for monopile wind turbine structures. So the first step in this process was to simulate a series of waves in OpenFOAM, which is a computational fluid dynamics software, using a Jean-Swap spectrum, which is an irregular wave spectrum based on real-world data. And then that calculated the particle velocity and position at the time of maximum wave height, and that gives you a graph just like this one here, which shows you the wave passing at its peak height. From this graph, I selected 8 key points to compare the period and amplitude of the waves, and I created a graph that looks like this, which has multiple different estimations of this irregular wave. So these are made using 2 different wave theories called Airy small amplitude wave theory and Stokes-Fifth-order wave theory. Then I calculated the total force and the moments acting on a wind turbine monopile structure from these simulated waves, and also from the estimations of those simulated waves through the existing guidelines. And that used Morrison's equation, which is given here. The coefficients in these equations, CD and CS, are given by the design standards. For my case, I was able to neglect the inertial term FM just based on the conditions of the simulation. So my expectation is that Stokes' fifth-order wave theory is going to produce more accurate results compared to Airy, because it has higher order terms that Airy does not include. So when I plugged that into Morrison's equation, it gave me a graph that looked like this. This shows in blue the CFD simulation, the force acting on the wind turbine as a function of the water height. And then these dotted lines here are the wave estimations from Airy theory. As you can see at the bottom of the water column, the force acting on the wind turbine is much overestimated compared to what CFD actually provides. And then when you look at above the water level at the peak where the slamming is at its highest, it really significantly underestimates the force. Now, this actually has an interesting effect. Despite it being a pretty poor estimation of the force at each height, it actually gets a pretty decent estimation of the total force when you integrate over the entire water column. Now, as a result of this, so 5 out of the 7 individual methods of matching period and height actually include the CFD total force within 1 quartile of their average. For the moment, it doesn't work quite as well. It's a little further off. But on average, across all 7 simulations, or all 7 estimation techniques, the total force was within about 5% of the calculated CFE force for each scenario tested. Now, when you look at Stokes force, you can see here at the bottom of the wave, it actually produces a much more accurate estimation of the force as the water height increases towards the still water level. But once you get above about the still water level and towards where the peak of the slamming force is, it's, again, way underestimated. So what this suggests is that perhaps the coefficient of slamming that was shown in Morrison's equation, given by the design standards, may be too low. So we may need to increase that to more accurately capture this high force from slamming. Again, when you integrate to see the total force and the total moment, what you end up finding is that it's actually much worse than area theory, which is a bit surprising considering it includes higher order terms in the wave. Now, as a result of that, none of the individual estimations accurately project the force or the moment. And actually, the total force is underestimated by 42%, which is quite a lot worse than area data. So in conclusion, what I found was that Stokes' fifth order wave theory really underestimates the force at every height and also the total force and the total moment, which is unfortunate considering that that's the wave theory that we use to currently calculate what the forces are going to be acting on these massive offshore structures. However, area small amplitude wave theory, which isn't currently used to the extent that Stokes' fifth is, while it may still underestimate the slamming force and the moment, it actually does provide a potentially useful estimation of the total force. And that could have some uses potentially doing working with the individual, the foundation of monopile structures. It could be useful there. Of course, there is still further research that's needed. We need to take a look at potentially changing that coefficient of slamming term more accurately capture the slamming forces. And then we also need to look at the accuracy of these estimations with varying water depth due to the constraints on the CFD system that we use. So yeah, now that I have talked about the impacts of water crashing into wave offshore turbines, Adriana will share her research on other ways that the environmental impacts of on wind turbines can occur.
Thank you. I'm Adriana Duran, and I'm going to talk about estimating wind turbine degradation over time in the UK. The wind energy capacity in the UK has been increasing the last year, especially in the last 10 years in the offshore sector, as you can see in the graph. Wind energy is one of the most important goals to achieve net zero goals for the UK government. So, but one of the biggest challenges is degradation. That is the focus of this research. Analyze the different patterns in the degradation in wind turbines over time, considering the factors that can affect their performance. To do this, we use a fixed effects linear regression model, the one that you can see in the top, and we use 3 different data sources. The first one was the wind farms output data from Option, the curtailment data from GREF, and the NASA wind speed and theoretical load factor from Renewables India. With this data, we calculate the actual load factor, the theoretical load factor, and use as fixed effects the site and the age of each of the 646 wind farms that we use in this study. In that map, you can see the location of each wind farm. The green ones are the onshore, the blue ones are the offshore, and the data period was between 2002 and 2023. The first results show a degradation in the wind turbines over time, but we want to know more in detail this degradation. So we decided to split the data. First, in type of turbines, offshore and onshore, and also we realized that during the data period, something unexpected happened, and it was COVID. And we know that during COVID time, there were disruptions in the operations and maintenance services of some of the wind farms. So we want to know if the COVID affects the degradation in the wind turbines. The results for onshore wind farms show a degradation of 1.17% per year, but also show different trends in the degradation. One at the beginning of the first 18 years of the wind turbines, then a plateau in 20 years, and after 25 years, a higher degradation. This is possibly due the 2015 de facto ban for new onshore wind farms and the sanctions for repowering older wind farms. That makes the company the opportunity to invest in older wind farms and add 10 more years of life. Also, we found that COVID affects degradation in wind turbines, but we are going to talk about that in the next slide. This whole degradation increased the LCOE for onshore wind farms in 11%. During COVID time, the degradation increased to 2.5%, which is really high. The good news is after COVID, the degradation reduced to 0.89. In the offshore wind farms, the degradation was 0.49%, which is lower than onshore. This is due there are newer installations and the conditions of the operations in the offshore wind farms are more consistent. Also, they were affected by COVID, but we are going to talk about that in the next slide. This whole degradation increased the LCOE for offshore wind farms in 4%. During COVID, the degradation was 0.62% per year for the offshore wind farms. It was less than the onshore, but the most interesting thing is that in the regressions in the post-COVID, the relative rate of degradation was positive. So that means that there was a really big improvement in the performance in the offshore wind farms after COVID. The conclusions are basically two. The first one is that there is a degradation in wind turbines. Onshore degrade faster than offshore. That is because offshore are more new and they will have better and more advanced technology. And the second one is that COVID accelerates wind turbine degradation. And this is really important to notice how vulnerable the sector is for this global crisis and the need to have better contingency plans in these cases. We have talked about one of the biggest challenges in wind energy, but harsh environments affect other important technologies too. Now, Michael is going to talk about the testing these impacts in carbon capture biomass.
Thank you, Adriana. Now, the previous two speakers have talked about water damaging and disrupting effects in wind turbines. We'll move on to another challenging environment in carbon capture pipelines, where water can be disrupting, can be dangerous, and we will try to use Raman spectroscopy to detect the presence of water in these pipelines, and if there is, we have to do something about it. So basically, carbon capture isn't really sustainable energy, but we heard this morning, carbon capture will be needed to remove all the CO2 from the air up to the numbers of billions of tons annually. As you can see in the UK electricity mix forecast, even in the future, there will still be natural gas in the mix of UK's electricity. That means we will still be generating carbon emissions in the far future. Aside from the energy industry, there's also other industries that are harder to decarbonize, like transport, in aviation. There's also buildings, agriculture, and the most is the manufacturing industry, the metals, obviously. And the question is, why don't we just stick carbon capture into every industry that we know? And the answer to that is the same answer to every question in life: money. Carbon capture, if it's added to the current energy mix in the UK, it'll increase the price of gas energy, the LCOE, even higher up, even more expensive than all other alternative energies. And especially after the invasion of Ukraine by Russia, the price will increase even more. According to the IEA, current carbon capture technology is at a point where the cost is at the peak, so we need to reduce this down for it to be commercialized. To reduce the cost, one of the ways is to reduce the risk that is involved with the technology itself. The risk can include carbon leakage to the surrounding area, water in the carbon dioxide pipelines, and also hazard from high pressure equipment. We'll be focusing on the water mix in the CO2 pipelines because it can cause erosion, which can destroy the pipes, and it can also create hydrates, which can block the pipes and cause it to burst. Now, we will detect this water using Raman spectroscopy. Now, some of you may not know what Raman spectroscopy is. It's the first time you've heard of the word. So basically, we'll take that instrument right there, the Raman probe, and shoot a laser at a gas vessel that simulates a carbon dioxide pipeline. Now, if you shoot laser at a gas, the obvious answer is, it'll just pass through the gas. What happens? Basically, a very small amount of the laser will be scattered by the gas molecules. An even smaller amount will be reflected back into the Raman probe for it to detect. And an even smaller amount is considered Raman scattering. Now, from this, you can tell the weakness of Raman spectroscopy is it can only detect a very little amount of the light that was sent out. But the advantage of Raman spectroscopy is that it can be used in situ. It can be used directly on the gas pipelines itself without having to take samples out of it. We'll basically use this to simulate, to try to, in an experiment using nitrogen and carbon dioxide with a mixture of water, and which will generate a spectrum where we can zoom in to find out if the peak area of the spectrum has any correlation to the concentration, and whether the peak position has any correlation to density. So basically, if we zoom in into the carbon dioxide and the nitrogen part of the Raman spectrum, we can see that for carbon dioxide, there is a linear correlation between its vapor phase density and the peak center position. It's very linear with an R-squared value of almost 0.9. But there is some deviations, especially in the higher density, which is on the right side. Now, this deviation is caused by CO2 acting in a more non-ideal gas and higher densities. And we have tried to use several ways to correct this. One of them is basically using the refraction index, which is linearly correlated to the density to see if it works. But sadly, with that, it makes the linearity even worse, so we decided to keep it this way. And with nitrogen, you can see that there is no correlation with this peak position. That is because nitrogen is a mononuclear diatomic molecule. It has a weaker intermolecular force, so it does not really affect the peak position. Next, if we look at the G2O, which we use instead of water, because our spectrometer is limited, it cannot detect water, it can detect heavy water instead. You can see that the peak area and the pressure is sort of linear to the vapor volumetric concentration. I say sort of because we can see there's lots of deviations, even though there is a side trend to be linear. Now, these trends often happen at higher pressures and lower temperatures because the water hasn't evaporated yet, and in the equilibrium, there's very little amount of water vapor, so the spectrometer wasn't able to detect them properly. So from here, we can conclude that there is potential for Raman spectroscopy to be used to detect water content in CO2 pipelines. However, more research will be needed to replace H2O with actually H2O, and more data sets to create a more accurate correlation between these data. Right. So now that we are finished with carbon capture in the industries, we move on to another challenging environment all the way to sub-Saharan Africa with Thomas.
Okay. Thanks, Mike. We have now seen how the presence of water can be detrimental in the case of carbon capture pipelines. However, the lack of water, and specifically drinking water, is also a major challenge. So let me take you to rural sub-Saharan Africa and present to you how we can account for population shifts in the design of voltaic water pumping systems. The access to a clean and reliable source of drinking water remains a prominent challenge across sub-Saharan Africa. As of 2020, approximately 50% of the 770 million people lacking basic drinking water services worldwide lived in this region. There's also just 1 in 2 people that have access to electricity. Photovoltaic water pumping systems tackle both the water and electricity access issues by providing clean groundwater through harnessing solar power. One major concern, though, is that future population shifts are likely to provoke changes in the demands on these systems. If these shifts are not foreseen and the systems do not adapt, they may not be able to meet the future water needs of their local populations. This thesis therefore aims to account for population shifts in the design of these systems. The case study was the rural village of Dogma in Burkina Faso, where such a system was installed in 2019. And the scope was focusing on interregional migration, so migration between the 13 regions of Burkina Faso. Now, there's a lot of information on this slide, but let's work through it together from left to right. The methodology centered around the development of two main models, the migration model and the photovoltaic water pumping system model, highlighted in blue. The migration model forecasts interregional migration and the total population of each region every year until 2030 under three shared socioeconomic pathways. The use of these pathways allows different possible future socioeconomic environments and levels of radiative forcing to be evaluated. These forecasts then form the inputs to the photovoltaic water pumping system model, which determines the effect on the water demand of the system in 2030, how the components of that system may need to change to meet the demand. The migration model development flowchart shows we use the GIS MCDA method to gain an initial understanding of the regions migrants may seek to enter or leave. More on this in the next slide. And the final output is a regression model developed in Python that is trained using historical data to predict the number of migrants between any two regions. Photovoltaic water pumping system model is developed in MATLAB, and it completes four main checks that are highlighted in blue. These are whether the solar panel array area and water tank volume are sufficient to meet demand, and whether the maximum input power and flow rate the pump can handle are being respected. So, the influences of several drivers of migration can be aggregated into a single metric called migration potential. And this is what is plotted on the map here, where higher values indicate the regions migrants seek to enter, the more blue regions, and lower values indicate those they wish to leave, the more red regions. The contribution of each individual variable towards this migration potential was determined from the strength of its historical correlation with migration. And we can see that this metric performed extremely well against the actual net flow of migrants recorded for each region in 2018, with a correlation coefficient of 0.89. So what does this show? It shows us that historical relationships between a small set of variables and migration can be used to predict the regions migrants may seek to enter or leave in the future relatively accurately. And this is exactly what is done in the regression model of migration, which is trained using historical data to actually quantify the future flow of migrants between any two regions. And here, the deviance metric is used to evaluate the model's goodness of fit. So how well the values forecasted by the model match those that actually occurred. We start with a null model where only a constant is used to predict flow. And then we iteratively add explanatory variables until reaching a final model that reduces deviance by almost 90% relative to a null model. And the table on the right shows the three most significant variables in explaining migration, were the dependency ratio, the conflict-related fatalities, and the wealth index of a region, and that overall, demographic variables explain migration best, followed by environmental variables, and finally, agricultural ones. For the case study of Ghana specifically, the results indicate that the current system installed will be sufficient to meet the demand forecasted in 2030 under all three pathways. For there to be an issue, there would need to be 45 new households using the system by 2030 relative to 2019. And in this case, an increase in the PV array area by a factor of 1.16 from 3.9 to 4.5 meters squared would be required to meet that demand. So, in conclusion, this thesis developed a methodology that consists of two models and could be employed by bodies responsible for the installation of photovoltaic water pumping systems, such as governmental entities or non-governmental organizations. By indicating how migration may influence the future water demand, the models can help ensure that both new and existing systems are sized accordingly. And this can help improve the reliability of these systems meeting their future drinking water demands. So, I've shown you how population shifts may influence the demand on these systems, but the groundwater supply on which these systems rely may also be affected by factors like climate change. So I'll now pass on to Amina to tell you more.
We are now going to change and shift the focus from population shift to climate change, and especially water resource availability. So to start, I just want to reemphasize that in sub-Saharan Africa, 14 million people don't have access to water, which means that 1 in 3 persons suffer from water scarcity. And coupled with that, 53% of the population don't have access to electricity. Therefore,
government and NGOs try to implement photovoltaic water pumping system as a solution as it tackles both problems. Solar energy is used to run the water pump and basically provide clean drinkable water to the population. However, climate change is not accounted for in the design and operation of photovoltaic water pumping system. And you may wonder, why do we need to account for climate change in the design of photovoltaic water pumping system? Well, Africa is expected to be disproportionately affected by climate change, even though they produce only 5% of the emission. And these effects are seen on the modification on the pattern of the population, as well as the increase on water strength and some abnormalities on water recharge and other African progress. Therefore, there is an urgent need to integrate climate change and especially water resource availability on the design of photovoltaic water. But how are we going to do that in this research? The first step of the research is the data collection, and this was the most challenging part, as there were not much available data on Burkina Faso. We collect climatic and hydrogeological data from the case study of Gogma, as well as from the University of East Anglia Climatic Research Unit and the MedCodex database. We use those data in Excel to develop scenarios, and after that, we implement those scenarios in the MATLAB model, in the Gogma MATLAB model, and simulate 3 different design modifications. After the simulation of the design modification, we analyze the results, and after that, a cost comparative resilience analysis of the new proposed PVWPS system and the existing one is issued. So, for the baseline scenario, we account for 4 main variables, which are the temperature, the rainfall, the recharge rate, and the groundwater level. The temperature and the rainfall data are divided into dry and wet season to facilitate the integration into MATLAB model, and as well because there is significant difference between the wet and dry season in Burkina Faso. For the first scenario, which is called the low impact scenario, which is equivalent to the representative concentrated pathway 2.6, we noticed an increase of 1.3 degrees Celsius in terms of temperature, an increase of 8% in terms of precipitation, and the groundwater level goes from 10.5 meters to 12.21 meters with some uncertainty due to the calculation of the groundwater level. For the mid-impact scenario, there is a slightly more increase. For the mid-impact scenario, there is a slightly much more increase, where the temperature increased from to 1.7 and the rainfall increased from 10%. For the high emission scenario, which is the most important one, as Africa is in most of the research, Africa is expected to face the high impact scenario. Most of the countries did not start their energy transition yet. We noticed that the temperature data can reach 41 degrees, and we noticed that the groundwater level goes from 10.5 to 12.88 and can reach 70 meters when you account for uncertainties. So those data are used and simulated in the MATLAB model. And in this MATLAB model, 3 main design modifications are operated. And those design modifications are the increase of the perimeter area, the increase of the depth of the motor pump, and the increase of the water depth. And you may ask why those 3 increase. Well, we chose those increase based on the socio-economic condition of the population. Therefore, too expensive and technical solutions that require algorithm-based are eliminated. So we noticed that in this case, for the case study of Gogma, the system is appeared to be sufficiently strong to withstand the projected impact of climate change. However, if the static groundwater level reaches 20 meters or above 20 meters, there will be a need to adapt the water pump, therefore the water pump by 5 to 7 meters. So to conclude, we can say that in the case study of GOMA, there is no need for a design modification on the PV area. However, we can implement some preventive techniques such as the cooling of the PV area. We saw in the high impact scenario that temperature can reach the 41 degrees Celsius. And further research are needed as in the scenario development slide, we saw that there were a lot of uncertainty in the calculation of the groundwater level. Now we are going to shift the focus from one challenging environment to another challenging environment with Lorenzo.
Thank you very much, Amina. And thank you all for still being here. And impressive. I know you're all tired, so I'm going to keep this light and simple. And fun. Yeah. So, little SpongeBob robot style, simple and fun. What is stuff like this? Okay. So anyway, we have seen with our previous speakers how external environments can impose significant challenges on the implementation of new technologies. But sometimes the environmental challenges can be found within. And by that, I do not mean to make a cheap philosophical statement on the hardships of the human condition, no. I mean it quite literally. The human body is a complex and fragile machine, and it has been the biggest challenge of the biomedical industry to marry the human body with technological devices. From pacemakers to automated drug delivery systems, most of these devices have one thing in common: energy storage. This is why I have chosen constant multiphysics, a finite element modeling software, to model hybrid microbatteries that are implantable with gel polymer electrolytes. And I will expand on that later, do not worry. Light and simple. So, what does a good implantable energy storage device have as its characteristics? It needs to be stable, it needs to be safe, it needs to be biocompatible, it needs to be biodegradable, it needs to be flexible, and many more. And guess what? It also needs to have a good power density and a good energy density. This is why we went for a hybrid system that couples the good power density of a supercapacitor with the good energy density of a battery. Now, for the cathode or the battery side, we went for a Prussian blue analog or PBA as the material because of its high pore size that allows for the good insertion and extraction of potassium ions, allowing for good redox reactions. And for the anode side, the supercapacitor side, we went for activated carbon, quite a common choice because of its good conductivity and its high pore size, allowing for good double layer capacitance. And we also doped the activated carbon with vitamin B2. Now you might ask, vitamin B2? And I would say yes. Vitamin B2. Because it has redox potential and it adds redox sites. And now, most importantly for my thesis, the electrolyte was chosen to be a gel polymer electrolyte to hold the two electrodes together without the need for outer casing and allowing for good flexibility without losing much of the electrochemical properties. So for the main monomer, DMA-MA was chosen for its biocompatibility. AIBN was used as a common choice as the initiator to start or kickstart the polymerization process. EGDMA was chosen as the cross-linking agent, which basically what it does is it allows different polymer chains to link between each other, creating a stable three-dimensional flexible mesh. And PBS, represented by the way here in yellow, out of the yellow dots, and PBS was chosen as the liquid electrolyte, containing the species that will migrate between the two electrodes because it mimics the ionic environment of the human body very well. Now, so two analyses were conducted, one heterogeneous and one homogeneous. For the heterogeneous analysis, SEM images or scanning electron microscopy images, light and simple, were taken of the internal structure of the MAE under varying concentration of EGDMA cross-linking agent. These pictures were then made binary and then converted to constant multiphysics, where different materials were applied to different domains, and it was put between two different electrodes. Now, as you can see right here, a mesh was created, a fine mesh was created, and as you can see from the complexity of this mesh, it was a computational nightmare for my computer. It was working over time, and potential gradient and electric field and many other parameters were extracted from this study to be then analyzed. And Another simplified axisymmetric homogeneous model was created to conduct more time-dependent and long studies that would be too computationally intensive to do on a heterogeneous model. So the model is actually quite similar, except that the polymer gel electrolyte is homogeneous. And so cyclic voltammetry, electrochemical impedance spectroscopy, or EIS, and galvanostatic charge discharge cycling were performed using this model under a varying porosity of the GTE electrolyte from 0.2 to 1. Now, for the results of the heterogeneous study, as you can see from the graphs here plotting the Maxwell capacitance and the total electric energy against the cross-linker concentration, an optimal concentration of around 2% was found to be best, as it combines a good absorption of the liquid electrolyte by the polymer structure, while still allowing for the species inside, or the ions, to flow between the two electrodes quite freely and diffuse in the electric field. Now, for the result of the homogeneous study, a porosity of 0.6 was found to be best, as between 1 and 0.6, little changes in the resistive behavior of the battery cell were found. Meanwhile, between 0.6 and 0.2, there was a much bigger change in the resistive behavior. And at this porosity and the scan rate of 5 millivolts per second, the specific capacitances of the cathode and the anode were found to be 178 and 238 farads per gram, respectively, for a weight ratio of 1.4. Now, to conclude, heterogeneous study says 2% cross-linker concentration, and homogeneous study says 0.6 porosity. Now, for the limitations, more experimental studies have to be done on this battery to verify the simulation results, and longer driving and cycling studies have to be done on the batteries also, as they were too computationally intensive to perform when it comes to multiphysics. Now, Dylan is going to talk about 2 different micro supercapacitors and the mechanical properties. Thank you very much.
No, it's been a long day, and I'm the last person standing between you and your clapping hand. Yeah, that's right. So, but don't worry, I will keep my presentation short and very quick. I think many of you guys have seen this movies from the Iron Man, right? Look at this power system. It's really cool, but this kind of system doesn't exist in the real world. One of the main problems is because law how mechanical factors affect implantable energy devices. Implantable energy devices always contact with human tissue. If these devices doesn't match the flexibility and stretchability of human tissue, it will cause a foreign body reaction. This study aims to evaluate 2 supercapacitors. By using finite element method, they will be tested under tension, compression, shear force, and filter testing. This is the first one is nickel-like, the second one is flammable. So they are provided by the PhD student Xu Ming. Thanks for him very much. And yeah, don't laugh at that. Okay, look at the geometry. The geometry is really small, right? Especially in the signals. So yeah, this is a flow chart of methodology. Once the problem definition is finished, a theoretical model is created and imported into Conzo. Then, finite element simulation has conducted, including structure design, like mapping, applying boundary condition, loading condition, and assigning material properties. Then the results of supercapacitor is compared with the ultimate stress and yield stress of material. The plant force is adjusted by the Gaussian section insertion method. Once the stress is matched, the particular testing is performed. Then all the results are analyzed for the recommendations. Finally, an application is introduced for demonstrating the practice use in the real life. On the right-hand side, this is how they look like in the condo. This is the result by applying tension, compression, and bending stress. As you can see, most problems happen on the metal and the interfaces of different material. Regarding the location first yielding and the location first failure, it can be summarized into three reasons. The first one is sharp corner and stress concentration. Like the stress concentration like in the short corner, such as in design, in the the gold current collector and silver coils, it's really easy to yield and failure. The second one is extremely thin metal layers. Generally, the thinner material has a lower resistance to the shear force. Therefore, increasing the thickness or adjusting the structure design can improve performance. The last one is interfaces between different materials. Stress concentration always occur at the interfaces of material with different properties, especially in the the elastic modulus or the shear modulus. So, which increase the risk of failure. This is resolved by performing fatigue testing. The weakest location is identified by the fading cycles. In the supercapacitor A, you can see the weakest location is the golden current collector and the substrate. The supercapacitor B, the weakest location is the interfaces between the golden current collector and the isolated insulation. On the right-hand side is the Ascent curve. S represents the applied force, N represents the failure cycles. So this is two supercapacitor Ascent curve under the action force and under the bending stress. Generally, supercapacitor A has performance than the supercapacitor B because it has more failure cycles under the same loading conditions. There are some limitations in my study. The first one is the bonding conditions. I use fully fixed for each layer, but it isn't in real life. It ignores the possibility of separation. The second one is the non-linear relationship in the high stress areas. I use a linear solver, so it could be some errors. The third one is matching for very thin layers. So you have to keep the size of mesh smaller than the thickness of layers, but there is a very thin layers, so it's quite challenging. Could be some errors. The last one is material property. All the material property from the literature, so it should be some difference in the experiment. In conclusion, I provide a finite element method to evaluate the mechanical performance of two supercapacitors. So as we finish this year's student conference, we have seen many different technologies. For the wind turbine facing a force to the implantable electronics inside our human body. We've seen how new ideas and teamwork can solve problems from the outside world to inside us. Thank you for being here, and we hope this presentation can give you some useful insights to understand how technology can succeed in this tough situation. Thank you, guys.
We can take questions now. That was great. Hi, Lorenzo. Thank you for this amazing presentation. I have a question for you. You mentioned something about using biodegradable material in biomedicine. And what I know in biomedicine that scientists use biodegradable material as a vehicle to transport or at least integrate whatever it carries on the human body. So could you clarify more? If we use a biodegradable battery, how could that end in the human body? And what are the effects on the human body? Maybe I misunderstood that.
No, you absolutely exactly right. So it ends in disintegration, just with time. But it's a very difficult process that I did not analyze in my research, but some PhD students I worked with are analyzing this. And it's actually a disintegration that is supposed to be timed. So you want your battery to work for a certain amount of time. So you would design your materials in a certain way that they would disintegrate in, let's say, 6 months, 4 months, 2 weeks. And yeah, it would just end up in you having a bit more vitamin B2 in your body. Great. So that's basically it. Thank you.
Thank you. So, Amina, so you mentioned that you found the data gathering really difficult because of the nature of the research. So what would be the next step to make this more like a systematic thing so that this can be repeated in other countries around the region? Did you look into that?
The thing that would be interesting to implement was is environmental mapping of the parent Africa, because actually there's a lot of oil company in Sub-Saharan Africa. So when doing oil survey, you can map the groundwater condition on when doing the oil survey. So when companies are doing oil survey, they should government should oblige them to do as well groundwater survey and provide data available for use for research like that.
Thanks. One quick question. Very interesting on the wind turbines, I suppose it was quite interesting to see that you'd established that there was an underestimate of the loading on offshore wind, and especially given the building a rollout around the world in all sorts of weird and wonderful places, including places with high energy seas. Did you notice in your work that this has been identified by the industry already, or to sort of, because the implications of underestimating these loadings, as was seen in the offshore oil industry, are quite significant. So, can you just comment on that, please?
Yeah, so you bring up the offshore oil industry, and actually a lot of the literature that I used in this project originated in the offshore oil industry. Morrison's equation, for example, was developed for offshore oil rigs in the 1950s. And yeah, so there is some knowledge that this has been sort of underestimated. And right now, one of the big things is, obviously, when you're designing really anything, you want to build in a safety factor. And so there have been previous studies, actually several previous years in SEF studies on the same topic, which have found similar findings, that there's an underestimation of the force of the loading due to slamming. And one of the things that our goal is to, more accurately reflect that, so that existing wind turbines, which are built with higher safety factors, which drives up the cost for wind turbines, especially offshore wind turbines, will then be more accurately estimated, so you can reduce the safety factor and thereby reduce costs for these structures. So that's sort of the overall goal of this continuing series of research projects.
Okay, thank you. That's a wrap.